Contiguous jump in time, Prim jarnik algorithm. So this is an algorithm for the minimum spanning tree that was discovered by Czech mathematician Jarnik in 1930. Now it was actually rediscovered by Prim in 1957 and rediscovered by Dijkstra again in 1959. And so because of this legacy, you'll sometimes hear this called Prim's algorithm because he was the first sort of popularizer of this algorithm. Sometimes it'll be called Jarnik's algorithm since he was actually the original discoverer. You'll also hear Prim Jarnik. Sometimes you'll actually hear DJP for Dijkstra Jarnik Prim. This is an example of this interesting phenomenon where the first person to discover something often doesn't get it named after them because they might have discovered it at a point in time and in history where the full application and the full utility is not fully realized. And so you can imagine Prim is working in an era when, albeit in a primitive form, there are in fact computers, whereas Jarnik is working in a time when he's really just working theoretically and as a mathematician. So there's not yet substantial practical implications of this algorithm. And so a little bit about the idea of a minimum spanning tree. This is a tree that will make all nodes reachable using a minimum cost subset of the edges. So from any node, you could reach any other node along these edges, and the total cost of all those edges added up together is minimized versus some other possible subset of nodes. Sorry, another possible subset of edges. Now, like Dijkstra's algorithm, we're also going to keep around a priority queue, and this priority queue will contain all of the edges, weighted by what the cost of the edge is, that connect to nodes that are not yet reachable from our tree. So we're going to have a set of nodes that are already included in our tree, and then obviously there's a set of nodes not included in our tree. And as we discover new nodes and add them to our set of nodes that are reachable, we're going to look at the edges from those nodes to nodes that aren't reachable, and we're always going to pick the lowest cost one of those edges. So this is a greedy example of a greedy algorithm. So here's our sample graph. I generated this randomly with some Java code using the graph package that you're going to be, or possibly are already in the process of implementing. We've got the nodes that we've solved. These are nodes that are already part of our minimum spanning tree that we're building up. We've got edges. These are the edges that are included in the minimum spanning tree. And then frontier. This is a collection of all of the edges from nodes that we've already handled to nodes that we haven't handled. And this is basically the priority queue. So to start with, we need to pick a node to start with. Now, all nodes need to be included in the minimum spanning tree because it, by definition, has to include every node. So just arbitrarily, I'm going to pick A, kind of start at the top here. So now A is included in the minimum spanning tree that we're building up. We don't have any edges yet. We just have the one node. So what we're going to do for our frontier, we're going to figure out, well, what can we reach from A that we haven't seen yet? Well, I can reach B, I can reach F. So we're going to put those into our priority queue, and we're going to pull out the lowest cost one. So it means we're going to put edge AF into our set of edges. So I'm going to go ahead and highlight this in red. This has been included. Now A and F are both included in our tree that we're building up so far. And we've gone ahead and we've sort of used this edge. Now F is in. What we're going to need to do is look at all of the things that F can reach that we have not already seen. So we're going to add those in, and the additions I'm going to do in blue. So from F, we can get to K with a cost of 1, and we can get to G with a cost of 16. We can also get back to A, but who cares about A? We've already seen that. So we're going to add these edges in. We're going to throw them into our priority queue, and then we'll pull out the lowest cost thing in our priority queue. Bam! So that's this edge FK. That edge has been included. We're going to highlight it here in red, and now we've solved AFK. Now K is a part of our minimum spanning tree, so what can we reach from K that we couldn't reach before? Well, we can reach L, we can reach P, we can reach F, but again, F we've already seen, so we're not going to add that in. So we've got an edge to L, we've got an edge to P, we haven't seen those before, we put those in. Same process as before, pull out the lowest cost one. Bam. So now we're going to go to L. That's the lowest cost edge that we have available to something that we haven't already seen. We're going to put that in red. We'll note that we've added it here. Now L is now in our minimum spanning tree. So what do? Well, what can L reach that we couldn't reach before? Well, L can reach G with a cost of 27. It can reach M with a cost of 25, and it can reach Q also with a cost of 27. So we put those in, they go into the right place. What do we pull out next? Well, if you notice now there's two ways we could reach G. We've got this FG edge and we've got this LG edge, but remember, since this is a priority queue, we're going to pull out the lowest cost one. So now we put another edge in, put that in red, add it to our list of edges, and G has been solved. So now what do? Well, what can G reach that we haven't already seen? Well, G can get to B. We haven't seen B yet. That's fantastic. G can get to H, cost of 16. We'll put that in. G can also get to L, but remember we've already solved L, so we're not going to add that in because that edge is never going to be part of the minimum spanning tree. So we pull out the lowest cost. That's B. Fantastic. B is now in our minimum spanning tree, so that edge has been solved. We add this, that node has been solved. This edge is added in. We're going to highlight it in red. Now from B, what can we reach from B that we couldn't reach before? Well, the only thing we can reach that we haven't already seen is C with a cost of 17. So we're going to add that into our priority queue. Now at this point, you can kind of see the game of what's going on here, right? Look at this. We've got A, we've got this edge, this edge, this edge, and then from here, this edge and this edge. We're starting to build up a tree, right? It's a directed acyclic graph. We're starting up, well, it's not necessarily directed, but it's basically a tree. We're starting here, and then we're building this stuff all out together. So there's no cycles are going to be in here because it's a tree, but it's not quite the same as a path, right? We can sort of go to here, but then we've also got this branch off of here. It's going to ultimately end up looking like a tree, and it's a tree that's going to include every possible node. So let's pull off the next node. Bam, GH. That's the cheapest thing that we have available to something we haven't already seen. So we'll pull that off. We add this edge. We add this. H is now solved. Fantastic. What can H reach that we haven't already seen? Well, HC, that's a cost of only 14. That's great. And then we've got also HI and HM, but those are costs of 29. We're going to put that in. And of course, this HC, we've now discovered a better way to get to C than we had before, because this is only 14, this is 17. Only one of those edges has to be in to join this node C in there, and we're going to get the best one. So we're going to get that. C is now solved. HC, this is added in. Now let's add everything that we can get to from C that we couldn't get to before, and that's only D. So this edge, CD, with a cost of 22, we're going to go ahead and put that in. We'll pull the cheapest thing that we have in our priority queue. Now, here's something interesting happens. Well, this edge, BC, this gets us to C. Well, C has already been solved. We already have C reachable from our tree. So we don't actually care about C. Anytime you pull an edge off of your frontier, okay, and that edge is to something that you've already seen, well, we'll just skip it. That's not something that we need to worry about. So we pull the next one off instead. That's actually gets us to P. So we'll put KP. That's the next best edge that we've got, and that brings P into the fold. So now we add this edge. P has been solved. What can we reach from P? Well, we can reach Q. We can reach U. So we've got PQ. We've got PU. Those are going to get added into our frontier. We pull off the lowest cost one. You can sort of see what's going on here, right? We're going to add this in, PQ, add that to our list of edges. Q has been solved. Now what can we reach from Q? Well, Q can get us to M, cost of 17. We'll add that in. And then Q can get us to U, cost of only 9. When we pull the lowest cost thing, that's what we get. QU, we can actually reach that. Now, we had PU with a cost of 12, but this is better. QU gets us there with a cost of only 9. So we add that edge in. U's been solved. Now, what can we reach from U that we couldn't reach before? Well, nothing. The only edge U has is an edge that other than the edge back to Q, which obviously we don't want to. We just did that. We have an edge back to P. Well, P's already been solved, so we don't really care about P. So there's nothing to add to our list. So we pull the next one out, and again, This edge, we don't care about this edge. We already had a way to get to P. P's already been solved, P and U both, so this edge, totally useless. We don't need it. We're going to throw it out. So pull out the next thing, QM. M we hadn't reached, so we're going to add this edge in, QM. M has been solved. We can throw that out. Now, what can we reach from M that we couldn't reach before? Well, we can get to I. Now, M can also get us to L and can get us to H, but L and H have both been solved, so we're not going to put those edges in because we don't really need to. So now we add in all of the neighbors of I. What can I get to? Well, we pull this edge off first, sorry. We're going to put MI in there. We've got I, fantastic. Now what can we reach from I that we couldn't reach before? Well, IE6. Oh, I just realized that's a pun. It's like Internet Explorer 6. Ha! I'm so funny. So IE6 and ID with a cost of 27. So those are going to go into our priority queue. We're going to pull the first one out, i.e., well, we'll add E to our list of nodes that we've solved, i.e., this edge gets added in. Fantastic. Now what can we reach from E that we couldn't see before? Well, ED with a cost of 22. Now this is actually really interesting if you think about it. We're basically done. The only thing we need to add in is node D, and if you look at this, well, we had CD with a cost of 22. We actually have ED with a cost of 22 as well. Now the question is, which one needs to go into the minimum spanning tree for it to be correct? And the answer is, it doesn't matter. This is very, very clear evidence at this point. We've run this entire algorithm. We've built up this minimum spanning tree. We just need to get this node D in. And in fact, at this point, we're going to need either this edge, CD, or this edge, ED. Those are both the lowest cost edges in our priority queue. It doesn't actually matter which one we put in. This leads us to a very important conclusion. Minimum spanning trees are not necessarily unique. There might be different sets of edges that you can build up to make a minimum spanning tree that will have exactly the same cost as some other minimum spanning tree with the same cost but a different collection of edges. It's completely possible. And, to think about this, suppose you have some sort of gigantic graph that's really densely connected, but the cost of every single edge in there is only 1. So it's a uniform cost for every edge in the graph. Now, we can go ahead and put together a minimum spanning tree of that. There might be many minimum spanning trees with the same cost because everything has a uniform cost of 1. So that gives you lots of different opportunities to pick different edges. And so this is just kind of a simple example of that. Either of these edges will work. It's just going to depend on how our priority queue implementation happens to be sorting them. So in this case, I happen to pick ED, so we put that in. We now have a minimum spanning tree. Right? Every single node is reachable from A, from any other node really. You can get to everywhere, and whatever the total cost, if we add up all of these edges that are listed in here or that are in red over here, whatever that cost is, that's the minimum spanning tree. Now there might be another minimum spanning tree that costs the same amount in this graph, but there's not going to be one that's better, because if there were one better, well, we already would have found it. And another thing that's very interesting about these this minimum spanning tree algorithm is it's a very good example of what's called a greedy algorithm. So at any given moment, we're just picking whatever the lowest cost edge from something that's in our set of solve nodes to something that's not in our set of solve nodes. We're just going to pick the cheapest edge. Whatever's cheapest. We're not going to think about it. There's no analysis we're going to do. We're just going to pick the cheapest one, and it's provable in this case using fancy mathematics that I've never actually even looked at the proof, but I know it's provable that that this greedy algorithm is optimal in this case. It's going to find the best possible minimum spanning tree in this particular graph. Now, there's a number of other algorithms, a number of other places in the world where you can have a greedy algorithm that is not optimal. And particularly as we talk a little bit more about artificial intelligence, and we talk about optimization problems and things like that, you're going to have a number of situations where greedy algorithms might be fast, they might be useful, there might be ways to tweak greedy algorithms to make them work a little bit better, but that they're not going to always be optimal in all situations. This is a situation, and in fact Dijkstra's is another situation, where a greedy algorithm happens to lead to an optimal solution, but that's not always going to be the case. Great, thanks for listening. Do I have any other slides? I guess I have an empty slide. Okay, good. We're done.